Recently, there has been some interest in the study of Artinian local rings because it is felt that they might play an important role in classifying Artinian rings. For instance, Artinian commutative ring is a direct sum of local rings. So let us first start the study of finite we will study first finite local rings. The plan of the talk, we will study first finite local rings, and then we'll study finite rings in which the multiplication of any two zero divisor is 0, and then we study finite chain rings, and then we study finite almost chain rings, and then we go and study the Artinian chain rings. Let R be a finite local ring, then and GR is maximal ideal, then R over GR is a finite field of order PR for some prime B and positive integers, and the order of R is PMR, P to the power MR, where the GR, the order of GR, the maximal ideal, is Pm minus 1R for some positive integer m. Now, GRm equals 0, and the characteristic of R is Pn for some positive integer n, with n between is greater than or equal to 1 and smaller than or equal to 1. We will call these integers Pm and R for finite local ring the invariant of
Khamis. Please, can you remember the definition of local ring?
Local ring is a ring which has unique maximal ideal. Let us call the integers B and Rm invariant of the finite local ring R. Now, if we have finite ring, then the following conditions are equivalent. R is a chain ring. Chain ring means all the ideals in the ring form a chain. So it has a unique chain of ideals. The ring is a chain ring if this is equivalent to R is a principal local ring. And this is also equivalent to that the ring is local with a GR principle, the maximal ideal is the principle. And the last condition, this is R is local and GR has maximal index potency. Now, we call the index of potency, you know, we already know that if R is a local, if R is local ring, finite local, then we already noticed that R is PMR, we have R over VR is finite delta field of order PR, and also the order of G is Pm minus 1R. B is Gm is equal to. Now, if gk equals 0 and gk minus 1 is not 0, we call k is the index of nilpotency of the ring R. So if the ring is chain, then this is equivalent that it has the maximal index of nilpotency. And this means that the index of nilpotency of finite cell ring, if it's chain, it will be m. So this is the last condition, that the ring has a maximal index. It's local and has maximal index of nilpotency. This is equivalent that the ring is chain. Now, of special interest is the ring when we take the finite local ring with the invariant P and MR. If R is finite local ring with this invariant. If we take M equal to N, in particular, we take M equal to N, then we call this ring, first let us see what's this ring. If N equal to M, this means that R is what the order of R is PNR, where Pn is the characteristic of the ring. This ring, actually, it will be isomorphic, the conception of the where Gx is a reducible mode P polynomial over Zpn, a reducible mode P and of degree R. So this ring is called Galvari. It's very similar to Galvari. Finality. This is called Galvari ring. And we from now on we just denote this ring by GR, P and R. You know the invariant of this ring, the Galvari ring, is 3, P, N, and R. These are very interesting rings because they play similar role to the finite field. To show this, let us go to the following theorems. Let R be a Galvari ring of the form G and R, GR, P and R, then R equal ZP and A, where A is an element of R of multiplicative order PR minus 1. Auto of R is a cyclic group of order R. R is uniquely determined by P and N and R. So it has a lot of similarity with finite field. Just these rings were first noticed by Krull, 1924, and then rediscovered by others. A subring, we notice that there is a lot of similarity between Galvari ring and the Galvari field. For instance, if we have R is a Galvari ring of the form GR, P and R, then S is Galvari subring of this of the form GR, P and S. If and only R and divide R, similar to the Galvari field. So there is a lot of similarity. And as we mentioned before, the automorphism group of Galvari is group of order R. Now, so a lot of people thought that there is almost identical properties. But I just, to prevent misuse of galvaring, I provide an example of a subring of galvaring, which is not necessarily galva. For instance, ZP and GR, if we take the smallest subring, we take this smallest. This is subring of galvaring up, but this is not galva. You know, so in general, subring of, it's only galva. The subring of galvaring is ring only galva if and only if it's principal. And this is this result published in Composito Mathematica. Let us define a coefficient subring of a ring. Since we are studying finite local rings, we call, in general, if we have Artinian local ring, let R be an Artinian and R naught be a commutative chain subring of R. Then R naught is called coefficient subring of R if R equal R naught plus GR and R over GR as a field isomorphic to R naught over GR. In this case, we call R naught a coefficient subring. And later on, we'll find out that this R naught, the coefficient subring of a local ring, play important role in studying the local ring. Actually, Clark proved that Clark proved that coefficient subring of finite local ring, coefficient subring of a finite local ring the variance P and R is galvaring of the form P and R. So the coefficient subring of finite local ring. To show what's the, I mean, we'll go to, let us see you know, this theorem explains the rule of the coefficient subring. If we have let R be a finite local ring with invariant P and Rm, and R naught is coefficient subring, which we said is galvaring of the form P and R, then there exists pi 1, pi e in GR, in the maximal ideal of R, and sigma 1, sigma 2, sigma e in automorphism of R naught, such that R naught will be direct sum of these R naught pi modulo. R naught, direct sum R naught pi 1, direct sum R naught pi e as R naught pi module, and pi I R equal R sigma I pi I for each R in R naught. Sigma 1 to sigma e are uniquely determined by R and its coefficient subring R naught. So R, we can express it as direct sum, as we notice in the theorem here, R naught, where pi 1 to pi e are elements of the maximal ideal GR. Now we want to give the construction and the group automorphism and the enumeration of finite ring in which the multiplication of any two zero divisor is 0. Finite ring. Now if we have finite ring, in finite ring we have certain property that every element either zero divisor or a unit. In finite ring. This is not in general not true, but only in finite ring. So if we have finite ring in which the multiplication of any two zero divisor is 0, this means that set of all zero divisor of the ring form an ideal, because multiplication of any two zero divisor is 0. This form an ideal and is the unique maximal ideal. So if the ring finite, the multiplication of any two zero divisor is 0, then this means it's a local, then R local, and GR equals 0. So we call this a ring with minimal index of normal tendency. The finite ring in which the multiplication of any zero divisor is 0. Actually, if we have this construction of construction A, if we have the ideals, the matrices, let us take this set. Here we have R0, R1, RE. Now, I am on the first column. Let S be either Gilbert ring of this form, or the Gilbert ring of order here. We assume S either Gilbert ring, because we have B square equal R, so the characteristic either P square or P. If the characteristic P square, we take the ring this. If the characteristic is P, we take this. Now, we assume R0 belong to S, and R1, RE belong to S. Now this, R0 plus GS, I'm sorry. Sigma 1. R0 plus GS sigma E. And these are zeros. If we take, then one can prove that if the ring, finite ring in which the multiplication of any zero divisor is 0, then the ring is isomorphic to one of the ring given by construction. And the number of mutually, this is the enumeration. The number of mutually non-isomorphic local ring with minimal index of rotancy, this means the ring with finite ring with fewer zero divisor, with a few zero. The number is R plus E minus 1. the number, as you see, where R is the residual order PR of the, and E is the number of pi 1, because we have, if R is a finite ring in which the multiplication of 1 0 divided by 0, I can write it like S as pi 1. We call this, before we use R naught, pi 1, this R naught pi E. And we associate with each pi an automorphism of R naught. We call this Dingo spaces. So here we have, in this particular case, actually we can put instead of S, because, so this is R. So if we take an element R naught plus R1 pi 1 plus R E pi E, we send this element, the correspondence matrix, will have an isomorphism. And the number of finite, mutually known isomorphic finite rings in which the multiplication of any 2 0 divisor is 0 with the invariant PRE is this number. This actually and also here automorphism of the ring. The automorphism of R is a ring in which the multiplication of any 2 0 divisor is 0. This is the automorphism. These results published in Archive des Mathématiques. Now the question, after we discuss this ring with minimal index of potency, I ask myself, what's the ring with maximal index of potency? And somehow come out that the ring with maximal index of potency is chain ring. If we take finite ring with the invariant PNMR, the ring is local, is a chain, if and only if the index of potency of R is M. So I start studying the ring with maximal index of null potency, which is a chain ring. Where actually, in his thesis, 1972, give the structure. Before he gave the structure, he proved the following result. There exists, since the ring is a chain, it has one chain, then the ring is a principal local ring, and so GR will be generated by an element pi, and G squared generated by R pi squared. And so actually now we have this result, that there exists a positive integer k such that PR is GRK, because PR is an ideal in the chain ring, and so since I have a unique chain, there is some positive integer k such that PR equals GRK. And then pi k is an element in GR. It will be P naught. So actually k is a root for this polynomial. And this polynomial is an Stein polynomial. The ring theorists know what is an Stein polynomial. It's very important polynomial. So this is result proved by Weret in his PhD thesis. Also, R naught pi isomorphic to R naught as a module for I equal to 1 to t minus 1. There is a positive integer t. And R naught by I isomorphic to R naught P, where P is the one of the invariant for I equal to t plus 1 up to k minus 1. What's t? T is equal m equal, minus n minus 1k. So this is what's t. Also, because now these distinguished spaces in the chain ring, we'll have R equal R naught, if R naught is the coefficient of ring, R naught by k minus 1. We have power of pi instead of pi 1 pi e. And so we have only one associated automorphism, sigma, associated with pi. And then sigma squared is associated with pi squared, and so on. And this associated automorphism is uniquely determined by R and R naught. And it's of order k dash. K dash divide k if n greater than 1, if the characteristic is of order Pn, n greater than 1, then k dash divide k. Structural theorem for finite chain ring. Later the finite chain ring, then R is a chain ring with invariant P and R dash, K dash M, if and only if R is isomorphic to this, where Gx is the Eisenstein polynomial and M is the index of potency. R naught x sigma is this Q polynomial ring. Actually, I managed to give another construction to the chain ring as ring of matrices. I have limitation on time, but this is the construction I gave. For instance, if I take an example, just to explain this, I take pi, I take ring of matrices. It's a little bit. Let me explain to you. But I just. If I take a ring of matrices as follows. Now, the first column, element of R naught, until t minus 1. This is t minus 1. From t, I will take R naught over Pn minus 1 R naught. From t, column t, until k minus 1. This is all. And multiplication is well defined because this is, if I multiply element here with element here, it's clear how can I multiply. Now I take 0, 1, 0, all 0, and 0, 0, 1, and all 0. And this is, I call it pi, left pi, and then 0, 0, 0, 1, 0, 0. All the time, one moving, one to the right hand side. The last this is PU naught, PU1, PUK minus 1. You know, I have phi k, I mean, if I have a chain ring, I have, it's P U naught plus U1 pi plus UK minus 1 pi k minus 1. So I use these U naughts, and I assume I have a Gauss ring of this form, GR, PNR. First column, second column, until the T minus 1 column, the element, this one is element of R naught. While this one is element of R naught, you know. The last, I can consider PU1 is an element, PUT is an element here, you know. And so this T, now if I take T squared, the row go up. This will be, you know, and this will move up, and I have pi squared. So this pi will be exactly the same rule as pi in the chain ring. And so I have, I can assume that, let us consider the following ring. R naught, I'm sorry, let me type it like this. R naught pi, where I equals 0 is the identity. It's not exactly the identity, it's identity up to T minus 1 of R naught. But then I will have in the diagonal the identity of R naught over Pn after D. So I have an I equals 0 up to K minus 1. This ring of matrices, you know, this is, I mean, it's actually additive group. I can consider this as the addition is similar to, but then I define multiplication. If I take R naught summation Ri by I, where pi is here, multiplied by Sj by j, I define multiplication like this, matrix multiplication. And I call this skew matrix. This is isomorphic to the chain ring. This is another construction because, you know, chain rings, a lot of people get interested more in chain rings because of the use of chain ring in codes theory. And in code theory, people need matrix more than the usual structure. I hope this will be useful in code theory. This is an, you know, I actually later on Clark also find the enumeration of Clark find the enumeration of all chain ring, mutually known isomorphic chain ring, with invariant Tn R K N, because in the case of commutative, we don't have K dash. With Kb equal to 1, he gives the enumeration of the ring, chain ring with this. But commutative chain ring, only commutative. So I try to generalize actually his enumeration to the case of non-commutative chain ring. So through my study, I find interesting chain subring of R. If R is a chain ring with invariant P and R dash, K dash M, non-commutative, then the centralizer of R naught in R is the only maximal commutative chain subring of R containing R naught. And also, because this is chain, GR1 is generated by K dash, where K dash is the order of sigma. And R1 as a ring, this is what we call distinguished basis. It's called the direct sum R naught by K dash. And the invariant of this commutative chain ring is the P and R dash K1M. The center of the ring, the center of the ring is equal R2. What is R2? R2, S is equal R naught sigma. The fixed subring by sigma of R naught. This is now, if I take R2, K1 is K over K dash. I mean, if K dash divide K, then it's K over K dash. So this is actually the center of the ring is equal S plus an ideal A, where A is either 0 or Gm minus 1 or 5 if K dash divide M minus 1. Now, I find out that two rings of T are isomorphic with the same invariant. They are isomorphic with the same invariant if and only Z of R isomorphic Z of T. If they have the same invariant. So the number, this is give me the enumeration of finite chain ring. The enumeration is equal phi K dash N, where N is the number of the ring with the same invariant as ZR. So I not only generalize Clark result for the non-commutative case, but in general, we know what's the number of commutative chain ring with invariant P and R. Then we know the actually the variant of R1. I know what is the number of the chain ring with the invariant P and R M K dash R. So we generalize Clark result for the non-commutative case. Now let us concentrate on the ring of characteristic P. If the ring is of characteristic P, then it's clear that the ring is isomorphic to skew polynomial ring over a field over the polynomial generated by xk, because P here 0 is the stable polynomial or the Now I actually managed to find the group of automorphism of chain ring of characteristic P, finite chain ring of characteristic P, And the enumeration, but the more important is the automorphism. Here, of the commutative, this is the finite commutative chain ring, this is the group of automorphism. And then I can use this to get the automorphism of a finite chain ring. This were published in Quarterly of Oxford Mathematics. This is maybe University of Oxford journal. Since finite principal ring of characteristic P, commutative, is direct sum of finite chain ring of characteristic P, we think that one can get the structure of the group automorphism of commutative principal ring by using our result. Now this is the enumeration, the number of non-isomorphic finite commutative chain ring with invariant. This is Clark and Lange enumeration. This is published in Journal of Algebra. The group of units of finite commutative chain ring is completely determined by Christina Yu. The group of units. Now, the question after that, I study the chain ring, I use, in the case finite ring in which the multiplication of one divisor divisor is 0, I have the following case: R, B, R naught. When R naught is the coefficient subring of R, it's scale variable. R naught pi 1, R naught pi e. This is, in this case, R naught is either characteristic P squared or of P. And so I ask myself, what is the ring this if I take a ring R and then I take S, where S is the chain ring, and I take S pi 1. In general, not a Gauss value, a chain ring. But I put the condition that that these pi I, pi e, pi I, pi g is equal to 0 for all ig. And it's interesting that these, if I consider the ring R, this and a letter of G, if I took this ring, let us consider the ring R over an letter of G. And let's assume this is chain ring S. I want to study what is this ring. What's R? Surprisingly, I find this ring can be written like similar to the, if I take the ring of matrices S0, S1, SE, and here I will use where these. Now this is, I can substitute for this by at least S, where F is equal to S over P. I'm sorry. I'm substitute F is R naught or S naught over P, where S naught is the coefficient subring of S, the chain ring. Now it will be the same if I take this S naught plus P S naught, sigma 1. S naught sigma E plus E. Now, if I take this, where S naught, you know, if I have an element here, it will be S naught plus S1 by 1 plus SE by E. Where S naught is an element of the chain ring S. It turns out that any almost chain ring, what I call this almost chain ring, is isomorphic to the one of the ring given by construction. So it's like the representation of the construction given to the ring with the few divider. In what we call it's a ring in which the multiplication of n to 0 divisor is 0. So this is what we call almost chain ring construction. This is actually a paper published by Mathematica Japanica. This is the structure. I give also the enumeration and also the group of automorphism of such a ring. This is the enumeration. You know, it's similar to the enumeration of finite ring enumeration multiplication multiplied by n, when n is the number of chain ring. And the group of automorphism is this. If I have almost chain ring, then the group of automorphism is now one may ask the question, how can we generalize this result to Artinian local ring? The only possibility is the following. We took R Artinian local ring. Let me call it U with R bar is absolutely algebraic. I need to put this condition. What we mean by due? Due ring is the ring in which every left ideal is right ideal, and vice versa. This we call the ring is due if the left ideal is right ideal. And what's absolutely algebraic? What I mean by R bar, I mean R bar is R over dr. Absolutely algebraic over its prime field. It's algebraic over its prime field. If we have these two conditions, we'll get similar result to our. For instance, if I take, let K be absolutely algebraic, then we know that K, this is already known result, is the union of ascending this finite field, ascending chain of finite field. This is if K is absolutely algebraic. Now, if I take the following ring, let us call it R0, union of P and I. These are galvanic, ascending chain of galvanic. This ring, this is actually work of Hanan and Sergey Singh and myself. This ring have the following property. First, GR0 piano. Second, auto of R0, isomorphic to auto of R0 over piano. And third, if I have R0 T notes, if and only if R0 bar isomorphic to T note. So this ring, we call it generalized galvanic. And it come out that if we have Artinian dual local ring with R bars absolutely algebraic, then its coefficient subring is this. Here. So this is the first step. Now, in the case of chain ring, if we have Artinian chain ring, we don't need to put U, because every ring there is right identity. And so, in the Artinian chain ring, it's enough to say the R bar is absolutely algebraic. If we have now, so in the case of Artinian chain ring with R bar is absolutely algebraic. Then we can generalize all the results in finite chain ring to this Artinian chain ring. We only have one condition, that R bar is absolutely algebraic. Now, the interesting thing is here, you know, if we have phi k equal, you know, because I have a chain of ascending chain, ascending chain of galvani, this means you know it belongs to one of these galvani. So there is one galvani which contain all of them. And so let us assume that we call, let's say, S naught is the galva subring of R naught, which contain all this. Now, then I have a finite chain. You know, if I take this as naught, so this is a galvani. See? And so every Artinian chain ring with R bars absolutely algebraic, there is a finite chaining associated to it. So I will call R dash. If I have R dash is the finite associated chain ring with associated to R. Now, if I have two Artinian local ring with absolutely algebraic, then R is isomorphic to T if and only if, you know, R dash is isomorphic to D dash. This is the associated, finite associated term. And R over dr isomorphic to T over T. So now the enumeration of Artinian chain ring, the group automorphism, all our results in finite chain ring can be transferred here to the Artinian chain ring with R bar is absolutely algebraic. just I want to check if I didn't forget anything. Yeah, I think I cover all what I want to cover. Thank you very much.
Thanks. It's a long trip of subject.
Well, I hope it makes sense to you, because some of you maybe have, I mean, his relation with the ring is not that strong.
From 1924 till today, right?
Yes, yeah, well, yeah, the references is here.
Yeah. Thank you very much.
Thank you.